Okay, if the product of two natural numbers is 0, then at least one of them is 0. Both of them can also be 0, but at least one should be 0. In particular, if n comma m are both positive, that is, if both are non-zero, then so is n cross n. Then n cross n is also positive. And this appears in the text as the second exercise. Okay. So now what is the meaning of zero-divisors? Should I say at this stage what zero-divisors are? I think it's better to keep this term just like this for the time being. When we discuss higher algebra, when we come across something called ring theory, there we will see what zero-divisors really are. Because in this very narrow scope, I mean, we just know what do we have? The system of natural numbers. We have both the operations addition and multiplication. We have proved the basic laws of addition. For multiplication, we are just going on with the laws, proving them. In this very bare situation, without having sufficient examples, we will not really appreciate the need for this term, or we will not appreciate the significance of zero-divisors. Okay, so this is something we will see in future when we study abstract algebra. Okay, or in specifically when we study ring theory. There we will see the significance of zero-divisors. For now, we just concentrate on the statement. Now this is something again what we already expect. When we multiply two natural numbers, that product is 0 if and only if at least one of them is 0. In particular, if both are non-zero, and that's what positivity means, okay, then the product is also positive or non-zero. So we now prove it. This particular result will be helpful for the things that are coming. Okay, so now for the proof, we first prove the second part. We assume that n and m are both positive. Okay, that's what I think we did, right? Let me just see it. So we first prove that n cross m is positive if n and m are positive. Okay, just now something else crossed my mind. Where is that remark? Okay, yeah, I can make the notation, yes. I can make this somewhat cumbersome notation simple. So instead of writing n cross m, you may have noticed this. I am going on writing n cross m. Another simpler notation is just simply writing nm, so that I don't have to use this symbol for multiplication explicitly. Why do we do this? For ease of notation, I don't have to write multiplication, the operation. Writing two things without anything in between them, in this context, it means that they are being multiplied. But I cannot do the same thing with addition, because then we will not know what we are applying, whether nm means n plus m or n cross m. So if we have two operations, one of them we can suppress for ease of notation, and we, according to the usual practice, we suppress the multiplication. And at this stage, I should also mention that we assume the usual precedence that multiplication gets over addition. So, and okay, that is also for ease of notation. What that means is this: when I write A cross B plus C, it means that I have to calculate this product first, and then with that I have to add C. This is the usual practice to save us from using unnecessary brackets or like this, which indicates that we have to first of all multiply A and B, and then with the result we have to add C. Since multiplication is assumed to take precedence over addition, it will be calculated first. So, and this does not mean A cross B plus C. This is not the meaning here, because here addition is to be carried out first. So because multiplication takes precedence over addition, and these things that we are familiar with, they are going to be assumed. Okay. In other words, you just assume the simple rules of algebra, the things of bracketing and all those things. So now I don't have to use n cross n. I recalled it, so that's why it felt somewhat awkward at this stage. Okay, so we first prove that nm is positive if n and m are positive, right? So suppose nm is not positive, nm is equal to 0. Okay, so we first suppose this, and then we see what we get from here. Or now if I follow this way of proving, that is hoping for a contradiction, I don't think I will get any. Now it should be proved using induction, but strong induction. You see here, this result I will prove by induction, but by using strong induction. Why? Because n and m are both positive, so none of them can be 0, right? So we apply the strong principle of induction on n, suppose on n. Okay, see, right now at this stage it does not matter on what variable we are applying induction, because we have already proved that multiplication is commutative. So nm and mn are same. Induction on n, keeping m a fixed positive natural number, keeping m a fixed positive positive natural number. So the first value of n will not be 0, it will be 1. Okay, so note that 1 cross, or I should not say cross or right cross, 1m is equal to, see, by definition, or what follows from definition is 1m is equal to m. We have already seen this calculation that we did after defining multiplication. So 1m is m, so which is positive, because it's given that m is positive. So the result is true, nm is positive when n is 1. Now we make the induction hypothesis, assume, not assumption. Assume nm is positive for all n, or should I write it like this? Assume km is positive for all natural numbers. Remember, we are applying the principle of strong induction or strong principle of induction, same thing. Some people call it principle of strong induction, same thing. Since we are applying that, so our induction hypothesis is the other one, the stronger one. Positive for all natural numbers k less than or equal to n. Okay. Then n plus plus m. By the definition of multiplication, this is nm plus m, right? Now nm is positive. Why? It comes from the strong hypothesis that km is positive for all k less than or equal to m. N, in particular, if you take k equal to n, you get nm positive, and m is also positive. So then this is equal to this, which is positive. Okay, why is this positive? This is positive because we have, you see, we proved one result, that the sum of two positive natural numbers is positive. This we proved in the previous section. So since we assume these things to be known, so we are not mentioning which result. You can go back and check which one it was. So this is positive. So this completes the induction. Okay, so we have proved that the product of two positive natural numbers is positive. Now we come to the first part, this one. N cross m is 0 if and only if at least one of them is equal to 0. This we now prove. Okay. Next, we prove nm is equal to 0 if and only if, that is the double implication, at least one of n and m is 0. One direction is trivial. That's easy to see. Okay, it is not trivial, but it follows from what we have already proved. If at least one of n and m is 0, then we have already seen that nm is 0. Okay, so if this is true, then this is true. Now we prove the converse. Conversely, assume nm is 0. Okay, now we have to prove that either n is 0 or m is 0. At least that should be the case. But we assume the contrary, or we suppose the contrary. Suppose n and m are both positive. In spite of that, we are having this. This is my supposition. Then, by the previous paragraph means this result. Product of two positive natural numbers is positive. Nm is not equal to 0. This contradicts our assumption. Nm equal to 0. So the supposition is wrong. That is, at least one of n or m is 0, and this ends the proof. The proof that the natural numbers don't have zero divisors. Right now, wait, let me just see the time. Give me just 1 minute. Yeah, I have time. Okay, if I don't keep track of the time, then I may lose my dinner. Okay, now here they have given the distributive law after this. I should follow the order, but ideally associative law should have come first. Anyway, so the next result is proposition 2, 3, 4. Distributive law. Law or laws, actually there are two, but in this case they are the same. In a more general case, they are not the same. So for any natural numbers A, B and C, we have these two things. A times B plus C is AB plus AC, and B plus C times A is BA plus CA. Now this particular law, see, so far what we have seen, the results so far have been of a singular nature, in the sense that some of the laws involved addition, some of the laws involve multiplication, and some of the laws involve order. Okay. Although there was one proposition which linked addition with order, that is, order preserves addition, or I think it was addition preserves order. I don't remember the actual phrasing, it does not matter. Now here we have so far not linked addition with multiplication. So this distributive law does that. Here we have both addition and multiplication, and this is the most basic such law that links these two operations. So, and one more thing is that you can see that since multiplication is commutative, if I prove this, then from that and commutativity of multiplication, I automatically have this. I can write this expression like this, b plus c times a. I can write ab as ba and I can write ac as ca. So only one of them needs to be proved, and we are going to prove this one. Okay, and for that again we are going to use induction, but induction on what? Induction on C. Fine. So we prove A times B plus C equal to AB plus AC by induction on C, keeping A and B fixed. Okay, and we should also mention the other one, B plus C times A is equal to BA plus CA follows from this one and commutativity of multiplication. Right? So now we are going to apply induction on C. Note that, so the first case is C equal to 0. See, having gone through so many induction proofs and we are going on using induction left and right, this may give us the wrong impression that induction is the only way to proceed whenever something comes up. This is because the things we are dealing with are apt for applying induction. I mean, they are prone to induction type of proofs because they involve natural numbers. As we go to higher and more complicated number systems, induction may not be the way to move forward. And now, because we can use induction, so we are using it as much as we want to make things easy. So note that, so the first case is C equal to 0. So A times B plus 0 is A times B, that is AB, which can also be written as AB plus 0, and this is equal to AB plus A0. What are the things we have used here? This calculation of course comes from the fact that C is 0. This one comes from properties of addition. We will now just vaguely mention them like that, properties of addition. This again is equal to this. Now here we have used the fact that A times 0 is 0. So we have the base case or basis. Now we assume the induction hypothesis. Assume A times B plus C is equal to AB plus AC for some C. AB plus AC for some natural number C. Then we look at the case when we replace C by its successor, A times B plus C C plus plus. Okay, what does this give me? A times, okay, B plus C plus plus is actually B plus C, its successor. Now, by something that we have already proved, while proving that multiplication is commutative, this is equal to the successor of, oh, not the successor, not just that, this plus A, yes. What have I used here? I am again repeating. While proving that multiplication is commutative, we have proved this, n cross m plus plus is equal to, again I am writing cross now, anyway, just bear with me for some time. This is what we have used here. Now here, this is where we need the induction hypothesis. So this is equal to AB plus AC plus A, right? Now we can separately think of this one, AC plus A, and what I am thinking is this. Applying the same thing here, I get, if I write C in place of M and A in place of N, I get this. So this is again the distributive law. When I have C plus plus in place of C, so this completes the induction and proves this identity. Sorry. From this we get this one. After that we have associative law, and that is, I think, again a proposition. So it is proposition 2, 3, 5. And now instead of distributive law, we have associative law. Or associativity. For any natural numbers A, B, C, multiplication is associative, that is AB times C is equal to A times BC. Now we will prove this. Okay, distributive law. Okay, distributive law was not an exercise, but this now is again an exercise. These things have been left unproved by Terry. He expects us to prove these things. Some people are frustrated by the lack of proof in Tao's notes, but they give us a lot of opportunity to think of those proofs on our own and come up with ideas, and this practice actually is what makes us learn analysis. The struggle that we go through actually helps us think of the ideas and think of the paths that we should take in such situations. Okay, so that's why lack of proof is sometimes very good. Sometimes it is bad, of course, but this is not one of those cases. So multiplication is associative. So we apply induction on A, keeping B and C fixed. So induction on A, I have already said this before, the variable on which we are going to apply induction, that is up to us. It depends on what we I mean, what sort of obstacles we come across while proving something. If some variable gives us problem, we try another value. Note that 0 times b times c. So I want the basis first. So this is equal to 0 times c is equal to 0. We have already proved 0 times in. Okay, this is not proved, this comes directly from the definition. And a times, oh not a is 0. 0 times bc is equal to 0, or I can write it in a single line itself. Why do I have to look at the other expression separately? This is 0 times bc. So we have the base case. Now we assume the induction hypothesis. Assume AB times C is equal to A times BC for some natural number A. Then A plus plus times BC. Here we can use the definition directly and we can write A times BC plus BC, right? Now associativity of, our induction hypothesis gives us A times BC is AB times C plus BC, right? Okay, now AB times the, yeah. Now let me continue the calculation here. Oh, this is why distributive law was proved before proving associativity, because you see, we are in a position to use the distributive law here. I can take C common out. It's because of the distributive law that I have already proved. AB plus B times C by the previous, by proposition 2, 3, 4. You can write here. Again, I can use the previous proposition to write like this. There is a reason distributive law comes before associativity. Now, we already know that A plus 1 is the successor of A. B times C. So this is just the associative law when we have the successor of A in place of A, yes. So this completes the induction and the proof. Associative laws are somewhat at this stage for this system of natural numbers, they are easy. This completes the induction and proves my result. Okay, the next one links multiplication with order. Proposition 2, 3, 6. Multiplication preserves order. Okay. I just checked if this is continuing to do the video. Multiplication preserves order. And what is the mean the statement is that it involves strict order. Let A, B, C be natural numbers such that A is strictly less than B and C is positive. Then AC is strictly less than BC. That's what we mean by preserving order. That is, the direction of the order does not change upon multiplying by C. So this proof, I think, it also uses no, it does not use induction. You see, induction is a method that is sometimes used when other tools are not involved. If we have other more advanced tools than induction, then they can be used. Okay, so we are given that A is less than B. Now recall one result from the section on addition. Since A is less than B, there exists a positive natural number